two sections, which will be covered in a single video because the material is extremely related to each other, we're going to talk about covalent, ionic, and ionic compounds and naming conventions of covalent and ionic compounds. And a lot of this is going to be done on the paper and not on the lecture notes. And I strongly recommend that you take notes as you go through. So the first thing we need to do is talk about what are ionic compounds and what are covalent or molecular compounds. Those are kind of interchangeable names. Electrons are transferred in ionic compounds to form a positive cation, a metal, and a negative anion which attract each other. So ionic compounds, not surprisingly, contain ions. Recall that ions are charged atoms. How do they become charged? Well, they gain electrons or they lose electrons. That's how they become charged. If something loses electrons, it has a positive charge. If something gains electrons, it has a negative charge. How is one going to recognize these ionic compounds? Well, they're most easily recognized because they contain a metal or a positive polyatomic ion, and we'll talk about polyatomic ion shortly, and a nonmetal or a negatively charged polyatomic ion. So if we look at some examples here, this is NaCl, sodium chloride. It contains a metal. You know it's an ionic compound. So this is an ionic compound with Na plus and Cl minus. This is magnesium hydroxide. Hydroxide is a polyatomic ion that we'll talk about in a minute. Polyatomic ion means ion with two or more elements. That's why it's polyatomic. So in this case it has an O and an H, and it happens to be a negative charge. So this is magnesium hydroxide found in milk of magnesia. Again, the metal is a giveaway that it's an ionic compound. Note that if magnesium were by itself, magnesium metal, it is not an ionic compound because it's not a compound at all. It's just magnesium metal and it's neutral. But in compounds, magnesium has a charge of 2+. Calcium carbonate, this is chalk, contains a calcium. Calcium is a metal on the periodic table, and carbonate is another polyatomic ion. It's a carbon, 3 oxygens, and it happens to have a 2- charge. So these are some examples of ionic compounds, which are easily recognizable because they contain a metal and a nonmetal, or a metal and a polyatomic ion, but the metal is the key factor. There's also NH4+, which is called ammonium, which is the only positive polyatomic ion that you're really responsible for. So you do have to watch out for that because ionic compounds can contain ammonium, even though they don't contain a metal, NH4+. And we'll talk about more about polyatomic ions in a minute. Covalent compounds contain 2 or more nonmetals. Electrons are shared. They're most easily recognized because they're not charged and they contain 2 or more nonmetals. No metal. So for example, water, hydrogen and oxygen are both nonmetals. No metal present, no charge. Therefore, this is covalent. Carbon dioxide, found in the air, of course, and in soda, to make it fizzy. This is covalent. Carbon and oxygen are both nonmetals and no charge. C6H6O6, which is glucose. That should be 12. It should be C6H12O6, which is glucose, and that is also a covalent compound. This is not glucose. It may exist, but it isn't glucose. So, the next thing we want to look at is forming ionic compounds. And I'm going to show you forming ionic compounds 2 ways. At the end of the last lecture notes, or lecture video, whatever, I showed a little bit about forming ionic compounds, and I want to continue that now. However, I promise that I will show you a slightly easier way of doing this in just a few minutes. So let's look at an example, a couple examples, okay, of forming ionic compounds. So if you'll recall back to the table that we went over before, where we had the groups, the Lewis structures, the ion charge that we had found, and we remember that lithium, which has 1 valence electron, also applies to sodium, also applies to potassium, so on and so forth down the group of the periodic table. This is something that we're going to need to refer back to. So using this information, we can start to understand how ionic compounds form. And first we're going to look at main group ionic compounds when we do this. So let's look at an example of sodium, which is in 1A, so it has 1 valence electron. And we're going to interact sodium with chlorine. I'm going to try to remember to draw them in red, which is in group 7A, so it has 7 valence electrons. And if you recall from the previous discussion, what is going to happen here is sodium wants to lose this one electron so that it can be like neon. So it loses its valence electron, and then it has core electrons that are just like neon. And chlorine wants to gain one electron so that it can be like argon. So this is a mutually beneficial situation. And what you end up with is Na with one less electron. I'm not going to show the core electrons. And now it has a plus charge because it's missing an electron. And we end up with Cl, which originally had 7 electrons. And now, I'm going to draw it in blue, it has an 8th electron. And having an extra electron gives it a negative charge. So this is a mutually beneficial situation. Sodium is more noble gas-like, chlorine is more noble gas-like. So therefore, this is stable, and this is sodium chloride, table salt, which you know is a very stable molecule. If you start a fire in a kitchen, you put sodium chloride on it to put it out if it's a grease fire, and you happen to have a lot of salt around. So that's because this is a stable molecule. So we have, at the end of the day, a plus and a minus, which are attracted to each other and can be written this way as NaCl. So this is an ionic compound. It contains ions. How do we know it's an ionic compound? We see the metal. That's a good indication that it's an ionic compound. How do we name this thing? Well, for the metal, you just name it sodium. And for the nonmetal, you name it chloride, ending in IDE. And in this course, you'll always be given a periodic table, and the periodic table that we give you has the names, so you don't have to memorize them, okay? So chlorine becomes chloride, and that's basically that. Let's look at another example. Let's look at magnesium with its 2 valence electrons interacting with, and I'm always going to forget to use the right color, oxygen, which has 6 valence electrons. So magnesium is looking to get rid of 2 electrons so that it can be like neon. And oxygen is looking to gain 2 electrons so that it can be like neon. Both can be more noble gas-like. So this is another mutually beneficial situation. Magnesium transfers 2 electrons to oxygen. Magnesium now has no valence electrons, but it's noble gas-like, so it's happy, but it's missing 2 electrons, so it has a 2+ charge. It's an ion. Oxygen, on the other hand, has gained 2 electrons from the magnesium. It's now happy because it has 2 extra electrons. It's noble gas-like, like neon. So now it has a 2- charge or a -2 charge. So magnesium is +2, oxygen is -2. These 2 things are attracted to each other. So plus attracts minus. What you end up with is MgO. This is recognizable as an ionic compound because it contains a metal and a nonmetal. And we can name it. Again, to name it, we say the name of the metal, magnesium. And we end the name of the nonmetal in "ide," so we call it oxide. So this is magnesium oxide. This is the ionic compound. Now let's look at combining these 2 ideas. Let's look at what happens if we interact magnesium, which has 2 electrons, with chlorine, which has 7 electrons. And you could probably see we have a bit of a mismatch. So magnesium is looking to get rid of 2 electrons, but chlorine doesn't want 2 electrons. Chlorine only wants 1 electron. So what's going to happen? So what's going to happen is magnesium is going to give that first electron to this chlorine. And this chlorine is going to be happy because this chlorine is going to be, oops, I knew I would do that in the wrong color. This chlorine is going to be noble gas-like because now it has its 8 valence electrons and a minus charge. But magnesium is not happy. So what's going to happen is there's going to be lots of chlorines around because any measurable amount of atoms is a huge number of atoms. So it's not that like there's just one chlorine around. There's other chlorines around. So maybe it could donate, and it will donate, its other electron to another chlorine. We then end up with, oops, I did it again, another chlorine, which now has its 8 valence electrons and a minus charge. And now we have an Mg, which has gotten rid of its 2 electrons, is noble gas-like, and has a +2 charge. So what we end up with is Mg2 plus and 2 Cl minuses. To write this as a formula, we write it as MgCl2. So we have MgCl2 here. We still name it the same way. We name the metal magnesium and the chlorine as chloride. Note, we do not use a prefix for dichloride. We don't call it magnesium 2 chloride. We don't call it magnesium dichloride. We simply call it magnesium chloride. So this is how we form ionic compounds. This is kind of the long way of doing it. But the reason that I show you the long way, if you will, of doing it is because it's understandable. This is why the electrons are transferred. They're transferred to make it molar noble gas-like. Once they're transferred, you form charged species that have opposite charges that are attracted to each other. It also illustrates the point that electrons don't disappear. Sodium doesn't form sodium plus by making an electron disappear. Sodium forms sodium plus by giving an electron to something else. Then chlorine doesn't form chloride by magically making an electron appear. It takes that electron from something else. But it's a mutually beneficial situation that forms these ionic compounds, which of course contain ions, which have pluses and minus charges. So that is basically what's going on here. A side product of this is, you'll notice that all ionic compounds are overall neutral. The overall charge on all of these is neutral because one electron was transferred. One thing's plus, one thing's minus. Cancels out. One thing's 2 plus, one thing's 2 minus. Cancels out. One thing's 2 plus, 2 things are minus. It cancels out. And we're going to take advantage in later cases, in a few minutes, of knowing that ionic compounds are neutral. But before we do that, I want to show you an easier way to look at this. So the first thing to note from before we show you the easier way is, for main group elements, we know the charges. If they're in 1A metals, this may not apply to hydrogen, but for 1A metals, the charge is +1. For 2A metals, it's +2. For 3A metals, it's +3. And I'm just reading them right from here. For 5A metals, or excuse me, 5A nonmetals, it's -3. 6A nonmetals, -2. And 7A nonmetals, -1. So these are the ion charges that we can expect based on the Lewis structures, based on the theory that we just went over a few minutes ago. Now, let's look at what we can do if we simply cross the charges. So we just did this one, but let's do it again. Magnesium chloride. So what we have is, we have Mg2 plus, and we have Cl minus. Bring the number, not the symbol, the plus or the minus, down in a crisscross like this. So the 2 goes with the Cl, the 1, because it's just the minus, goes with the Mg. If it's 1, we don't write it, just like we don't write it here, we don't write it here. MgCl2. Notice that is exactly the same thing that we got, move this up a little bit, when we did it out this long way. So this is kind of a shortcut. You write the charges on the species, and then you cross them. I should have pointed out, magnesium is in group 2A, and chlorine is in group 7A. So magnesium is +2, chlorine is -1 when it forms ionic compounds. Let's look at another example. And again, these examples are on some of these examples, many of these examples are on the lecture notes, but I'm not going to just show the lecture notes. I want to show you how this works. So here, we're going to look at sodium oxide. So, step 1, find the elements. Sodium is here, And the more you do this, the quicker you'll find these things. You get used to where they are. So sodium is here, so it forms Na plus in ionic compounds. We know this is going to be an ionic compound because it contains a metal. And oxygen is here, so we know that oxygen is 2 minus. Cross the charges. Just bring the numbers down. And what you end up with is Na, the 2 comes down, and for O, the 1 comes down, and if it's 1, we don't write it. So sodium oxide is Na2O. Notice, I did not need to write any of this stuff to figure that out. You could do it this way, and it's important to understand it this way because this is why this other way works. However, you don't need to do it this way. You can do it this way. It's faster. Okay, let's look at another example where this actually causes a bit of a headache. Magnesium oxide. Now notice, when we formed magnesium oxide before, magnesium gave 2 electrons to oxygen. Now magnesium was 2 plus and oxygen was 2 minus, and these were attracted to each other, and this is what we ended up with for magnesium oxide. Watch what happens when you do it this way, though, with crossing the charges. Magnesium's here in 2A, so it's plus 2, or 2 plus. Oxygen is still in 6A, so it's 2 minus. Cross them. And what you notice is you get Mg2O2. If there's a common denominator between these, you need to simplify it. One way of thinking about this is the formulas of ionic compounds are empirical formulas. So you need to simplify this, divide them both by 2. And the formula you get is MgO. So if there is a common denominator, you do need to simplify. You'll notice that when we did it this way, we got MgO. It is not Mg2O2. All right, it is MgO. You have to simplify. Let's look at another example like that. Let's look at aluminum nitride. So we have Al 3 plus, N 3 minus. Cross them, cross them. We get Al3, N3. Again, there's a common denominator. Cross it, and what do you get? ALN. So this is how we are finding the formulas of ionic compounds. Note that everything we've done so far are these main group ones, 1A, 2A, 3A, 4A, 5A, whatever. The main group. We've skipped the transition metals and the metals underneath the nonmetals. And these play by slightly different rules that we are going to consider in a few minutes. However, before we consider the slightly different rules that these play by, what we want to look at is some polyatomic ions that don't really play by different rules. They just happen to be polyatomic ions. So these are polyatomic ions that you need to know for your test. There are other ones that may appear in your homework, and you can look those up in the book. In this section, there's a whole big table on them, and there are lots of polyatomic ions, many more than are on that table, but these are some of the polyatomic ions that you actually need to know for the test, that you need to memorize, essentially. So what are polyatomic ions? Well, polyatomic ions are exactly what they sound like. Polyatomic means many atoms, 2 or more. Ions means has a charge. And when you're learning these things, which I suggest you do by writing them down, you want to be super careful. So chemistry at times can be a picky thing where you have to be really careful, and this is one of those times. So if we look at phosphate, this is a polyatomic ion. It contains a phosphorus and 4 oxygens and has a 3 minus charge. Notice that this number is subscripted, which means that it has 4 oxygens. This number is superscripted, which means the charge is 3 minus. This matters very much. In this case, you have NO3 minus. This is a nitrogen bonded to 3 oxygens with a negative charge. If you write NO and the 3 minus is all superscripted, that means a nitrogen bonded to an oxygen with a 3 minus charge. That is not the same thing. So when you learn these, you need to learn them exactly as written. So in this case, acetate is C2H3O2, that minus should be better superscripted, or you can look at it as CH3CO2 minus, where it is more clearly superscripted. In carbonate, that should be a minus. I missed that. So this is CO3 2 minus. Sulfate is SO4 2 minus. Sulfite is SO3 2 minus, so on and so forth. An important thing to note is ammonium. Ammonium is NH4 plus. What's important to note about it is it's a cation. So ammonium is an example of a compound that cannot contain a metal and still be ionic if it contains ammonium. So let's switch back over to the paper and do a few examples. So let's say that we have carbonate, which I messed up on there. Carbonate is CO3 2 minus, and I'll try to fix that on your slides. So we have carbonate, which is CO3 2 minus, and let's say that we're going to make it sodium carbonate. All right, so we want to make the formula of sodium carbonate. Notice I do need to know that this 3 is subscripted and this 2 is superscripted. So sodium carbonate. First thing you want to do is find sodium. Sodium is Na plus. Carbonate is what it is. It's a carbon, 3 oxygens with a 2 minus charge. Cross them. And what you end up with is Na2, because this 2 comes down, CO3. This is the formula of sodium carbonate. So the polyatomic ions, which you essentially need to memorize, behave exactly the same way as the monoatomic ions. You just have to memorize what they are. You can't look at the periodic table and find their charge, or there's no carbonate on the periodic table. You won't know it's carbon and 3 oxygens. Let's look at something else that can happen. Let's look at something like calcium nitrate. All right, so nitrate is NO3 minus. You can look at the slide that you were given, and nitrate is on there, and you can find that it's NO3 minus. Calcium is a 2A metal, so it's Ca2 plus. Cross the charges. And here's where polyatomic ions are different. If you do this, you could write it as Ca1 NO3 2. And if you write it this way, this says a calcium, a nitrogen, and 32 oxygens. And this is not what we mean. What we mean is a calcium and 2 nitrates. So if you need multiple polyatomic ions, you need to put them in parentheses. And that's the fundamental difference between polyatomic ions and monoatomic ions. Let's look at another example of a remarkable one. Ammonium let's do ammonium carbonate. Just a made-up example. So ammonium is NH4 plus. Carbonate is CO3 2 minus. Cross the charges. Since we need more than one ammonium, we have to put it in parentheses. NH4 2 CO3, ammonium carbonate. What's remarkable about this compound is it doesn't contain a metal. Ammonium is the only polyatomic cation, the only positive one. You always need a positive ion and a negative ion. As I mentioned before, all of these ionic compounds are neutral. So that's basically how this system works. So these are some examples with polyatomic ions. Next, I'd like to look at some examples where we have transition metals. And transition metals are a little bit strange because they can form multiple charges. And let me show you exactly what I mean. So this compound, CuCl, exists. You can buy it from a chemical supply company. This compound, CuCl2, also exists. You can buy it from a chemical supply company. So we can't call both of these copper chloride, because if we call them copper chloride, then we're going to have a problem. If we order some copper chloride, maybe we get this one, which has very different reactivity than if we order copper chloride and we want this one. So they can't be the same name because they're not the same thing. They have very different properties. It may seem surprising that adding one extra chlorine changes it, but it changes copper from +1 to +2, which vastly changes its chemical properties. So we need to be able to name these things. And what we do generally for transition metals, these ones, and the metals underneath the nonmetals, so tin, lead, bismuth, these ones, okay, is we put a Roman numeral in the name. Now, it is not true that we need to put a Roman numeral in all of the names. For whatever reason, for example, silver is only known to man today to form +1 charges. That isn't to say that someone in a lab tomorrow couldn't make a silver +2, or maybe it already has been made, I'm not sure. But we consider it as only +1. So these rules are not 100% accurate, but I do want to simplify the rules. So for you guys, any of these transition metals or metals under the nonmetals follow these same rules. The representative elements follow the rules that we just talked about. Those are your A's, 1A, 2A, 3A through 8A. Okay, so now we're going to use these Roman numeral rules. So what you need to do is you need to add a Roman numeral in order to write the names of these things. And that Roman numeral tells you the charge on the metal. So let me give you an example of one. One example would be nickel 2 carbonate. This would be the name of a compound, nickel 2 carbonate. This Roman numeral 2 tells you the charge on nickel. So if we want to draw this, the formula, we know that this is Ni2+, and carbonate, you may or may not remember, is CO3 2-. Cross them. And intermittently, we end up with Ni2, CO3, 2. But, because they're both 2, we need to find the lowest common denominator, and nickel 2 carbonate is NiCO3. So the Roman numeral tells us the charge on the metal. But what if you have to go backwards? In this case, we're not given the charge on the metal, but we do know the charge on the nonmetal, and we do know the charge on the overall species. So the general formula is charge on metal plus charge on anion, which will either be a nonmetal or a polyatomic ion, equals 0. This is the formula that we want to use. So let's look at this example. So I should, to be clear, anions, because in this case we have 2 anions. So in this case we have copper, which we don't know the charge of, this is the variable, plus the charge on chloride. Well, chloride is main group. It's in 7A. We know its charge. It's -1 equals 0. Add 1 to both sides. Cu equals +1. The name of this species is copper 1 chloride. Let's look at this example. Here we have copper plus, there's 2 of them, 2 times -1 equals 0. Copper minus 2 equals 0. 2 times -1 is -2. Add 2, add 2. Copper equals +2. This one is called copper 2 chloride. So this is an example of how you would find the Roman numeral if you're given the formula. This is how you would find the formula if you're given the Roman numeral. So now, the last thing I want to do is address a question that I commonly get. And what students tell me is, well, why not just reverse them? If this is 1, this must be +1. And if this is 1, this must be +1. And that's true, except that sometimes you have to simplify. And there is the problem. So let's look at this one. SnO2. Now, tin is not a transition metal, but it is a metal underneath the nonmetals, so it can form multiple charges. So SnO2, we might say, well, it's tin 2 oxide because there's a 2 there. But let's actually figure it out. Let's use the math. The charge on tin plus 2 times the charge on oxygen. Oxygen's in 6A, so it has a minus 2 charge. So 2 times minus 2 equals 0. Tin minus 4 equals 0. Tin equals plus 4. The name of this compound is tin 4, which is IV, oxide. So we can't simply reverse them because sometimes we do cross them out and it's not obvious whether you cross them out or not. There's no clear way to tell without doing this math. Important to practice a few of these because this can be a relatively challenging thing to do, naming compounds with transition metals in them. Okay. The next thing that I want to look at is the covalent compounds. So covalent compounds are compounds which contain between 2 or more nonmetals and are named differently than ionic compounds. So some of these covalent compounds have common names like water or ammonia. And others of them, which do not have common names, we use these prefixes. So the first thing to do for naming covalent compounds is to determine whether or not a compound is covalent. And it's covalent if it contains 2 or more nonmetals and it doesn't have a charge. Of course, if it has 2 nonmetals and a charge, it's a polyatomic ion, and then it has whatever the name of the polyatomic ion is. So these are basically how you would do this. So if you look at CO2, this is carbon dioxide. Notice that for the first atom, you don't use the mono prefix. So the first atom, you name the element, just like you were doing with the metals, in this case carbon. And then, because there's 2 oxygens, we put the di prefix. The prefixes are listed on this table. And then we put oxide. If you have the second one, we have carbon monoxide. So carbon monoxide is the name of this because we have 1 carbon and 1 oxygen. So essentially, if the second element is only 1, you use the mono prefix, but you don't use it for the first one. So we just simply name carbon, and we change oxygen to oxide, and we do carbon monoxide. P2O5. This one, 2 phosphoruses, so diphosphorus. Again, we just use the whole name of the first element, and then we add the second element in ide. So pent for 5, like the pentagon, pentoxide. Sulfur trioxide, SO3, and nitrogen dioxide, NO2. So the general rule, name the first element, use a prefix if there's more than 1. Name the second element, use the mono prefix if there's 1, and the other prefixes if there's more than 1, and end it in IDE. So very similar. At the end of the day, though, on the exam, it's not going to give you something like, please name this covalent compound using the prefixes. And that's where this table comes in. And I strongly recommend you copy this table down. And this table is kind of a flow chart for how to name things. And we are going to use this flow chart in a few examples. So the first question you want to ask yourself is, does the compound contain a metal or a polyatomic cation? And as we do this, I want to do an example. And the example that I want to do is CrCl3. Okay, so we're going to do CrCl3 using this table. So does the compound contain a metal or a polyatomic cation? The answer is yes, it contains chromium, which is a metal. So if it was no, you'd use the prefixes, name the first nonmetal and the second nonmetal ending in ide. Use prefixes to indicate the number of each because it's a covalent compound. But this is ionic. And the question is the metal capable of forming multiple charges? Generally, this is the transition metals and the metals under the nonmetals on the periodic table. So we want to see, can chromium form multiple charges? Well, chromium is a transition metal. So yes, it can form multiple charges. So here is the yes. Name the metal, then the name of the nonmetal ending in "ide," and then it says use a Roman numeral to indicate the charge on the metal. So using this flowchart, what we find is, yes, it's ionic, and yes, we need to use a Roman numeral. So we need to find out what the Roman numeral is for this particular one. To do that, we have to do a little bit of math. So it's chromium plus, we have chlorine here, which has a -1 charge, and there are 3 of them. 3 times -1 equals 0, the overall charge on all ionic compounds. Chromium minus 3 equals 0. Chromium equals plus 3. So the name of this compound is chromium 3 chloride. And the flow chart let us know that we needed to use the Roman numeral. Let's look at another example. Let's look at CaCO3. So in the case of CaCO3, the first thing you want to ask is, does it contain a metal or ammonium, a polyatomic cation? The answer, of course, is yes. I apologize for keep flipping back and forth. It contains calcium, which is a metal, which is right here. So yes, it contains a metal. The next question is the metal capable of forming multiple charges? And the answer here is no, because it's in main group metal. It's 1A, 2A, or 3A. So no, it can't form multiple charges. So in this case, unlike the previous case, we go to this side because the answer is no. Name the metal, then name the nonmetal ending in "ide." So here you don't have to do any math. You can simply call this calcium carbonate. We do not use the nonmetal ending in "ide," of course, because it's a polyatomic anion carbonate. So this one's just calcium carbonate. Let's look at one last example, and not surprisingly, it's going to be a covalent compound. Let's look at SO2. Okay, so SO2. The first question is, does it contain a metal? No, it does not contain a metal. So this is a covalent compound. So we name the first element, sulfur. And then we add the prefix, because there's 2 oxygens, and we end it in "ide," dioxide. And this is how we name the compounds. On Mastering Chemistry, on the test, it's not going to tell you which naming scheme to use. So it's extremely important to get some practice using this table as you're doing your homework. I strongly recommend you either write it down or print it out and use it as you're doing your homework so it becomes second nature. The very last thing that I want to talk about here is naming acids, and I put here a brief guide. So this is not all there is to know about naming acids, but you do use acids in the lab, and you will talk about acid-base chemistry more in general chemistry too. So I do want to briefly mention naming acids, but I'm not going to get into great detail, as much detail even as there is in the book. So the first thing is, you may have heard of hydrochloric and hydrobromic acid, which have this prefix hydro. Well, this prefix is used for monoatomic acids. Monoatomic means just one atom. So the only atom here is chlorine. The only atom here is bromine. So the acids act as proton donors, H pluses, and start with hydrogen in their chemical formulas. So you'll notice that the H is sort of like a metal here, and it's interacting with a nonmetal. Although these are covalent compounds, because it is 2 nonmetals, they do act like acids. So they're proton donors if you've studied acid chemistry before. So in this case, if you have an H with a monoatomic ion, you use hydroic acid. So since it's chlorine, it's hydrochloric acid. If it's bromine, it's hydrobromic acid. What about polyatomic ions? This is one convention, and there are others that I'm ignoring here because, again, this is a brief guide. Here we have the sulfate ion, and 8 anions that end in 8, become ic acids. So sulfate becomes sulfuric acid. Notice there's no hydro. The reason that there is no hydro is because it's a polyatomic ion sulfate. It's not a monoatomic ion chlorine. Still two H's. Okay, this one has one H because this is plus 1 and this is minus 1. This is plus 1 and this is minus 2. So there's two hydrogens here. But sulfate becomes sulfuric acid. Phosphate, PO43 minus, which of course has 3 H pluses, becomes phosphoric acid, and nitrate becomes nitric acid. Notice, again, the lack of the hydro. So this is a very brief guide to naming acids. There's a lot more to it than this, but we're not going to go into that here, nor will that be on the test.